The next section we're going to take a look at is RF math, or radio frequency math. So to begin with, let's take a look at, as I mentioned in the last module, frequency and wavelength, just simple math. So the constant in our equation is the speed of light. So technically 299,792,458 meters per second. You could abbreviate that to, most people abbreviate it round up a little bit for a rough calculation, not for a precise one. Obviously, you'd use the actual number, but for a rough calculation, people tend to say 300 million meters per second. And that's going to be represented in our equation by the letter C. Lambda is the symbol, universal symbol for wavelength, and frequency will be represented with an F. So our simple calculation to find out to find out frequency would be, if we know what the wavelength is, we simply take the speed of light and divide that by the wavelength, and that will give us the frequency. Remember how I said if you know the frequency, you can find the wavelength. If you know the wavelength, you can find the frequency. So if we know the frequency and we want the wavelength, we simply take the speed of light and divide it by frequency, and we get the wavelength. And I put a little link there to a very easy but precise to use frequency to wavelength calculator online that I like to use. Okay, so some very simple math there. Taking a look at power or energy. So to begin with, we have the concept of Newton, joule, and a watt. So a Newton is the required force to accelerate 1 kilogram of mass to 1 meter per second. A joule is the amount of energy consumed by the force of 1 Newton moving 1 meter in a single direction in a second. So 1 joule is essentially the amount of energy needed to produce 1 Newton. 1 watt represents 1 joule of energy per second consumed. Okay, so 1 watt is really 1 joule of energy to produce 1 Newton. Just to give you an example, kind of some, real world relevance, breathing is roughly a 40-watt exercise. Climbing the stairs or climbing a ladder takes approximately 200 watts of energy. It's also something that you may have, especially if you come from an electrical background, then you have, and by that I don't necessarily mean electrical engineer, which goes into this and well beyond electronic engineer, but when I mean like traditional electrical background, like AC, alternating current, DC, direct current, that types of thing, home wiring, things like that. You're probably used to, although it's a oversimplification, you're probably used to understanding that volts times amps equal watts. Okay, again, an oversimplification for alternating current circuits. At any rate, 1 volt times 1 amp in a pure electromagnetism, realm of thinking or conceptually talking equals 1 watt. So 1 milliwatt is equal to 1,000th of a watt. So this is 10 to the power of -3. Don't confuse that with 10 to the power of 3, which is 1,000 watts. 1,000 watts is a kilowatt, but 1,000th of 1 watt is a milliwatt. We measure power to our access points in milliwatts, and they can often go up to 100 milliwatts, but we rarely use that much energy. We'll talk about why later. It largely has to do with regulation. So some examples of milliwatts are things like a laser pointer that uses around 5 milliwatts. A hearing aid uses less than 1 milliwatt. So we've looked at power and energy. We now want to take a look at exponentiation and logarithms. Now, this might, depending on your background, you might say, yeah, I remember this stuff, or I use it every day, or that was, high school algebra, which it really was. I don't really think this got into calculus. It was really more high school algebraic functions. But you might also not like math at all. I'm going to try to make it really simple for you, because I know that sometimes, people don't necessarily, just depending on your background, Most engineers don't tend to mind it too much or really love it as I do, but some people really hate math. And you might be worried, wait a minute, do I have to know this for the test? Well, you do have to know some of it for the test. So it's important to understand. There are probably a few key values that you could pick out from what I'm saying as we'll go on and talk about that, you'd be tested on versus you're not going to be given probably a number and forced to come up with the logarithm or something like that to it, but it's still important to understand. So exponentiation, or sometimes referred to as powers, it corresponds to repeated multiplication. So if I have 10 to the third power, or 10 to the exponent of 3, that is 10 times 10 times 10, right? 10 times 10 is 100, and then 100 times 10 is 1,000. So 10 to the third is 1,000. A logarithm is really a unit of measurement that was derived in order to simplify math equations and basically be the opposite of exponentiation. So a logarithm is the exponent by which another fixed value, which is referred to as the base, has to be raised in order to produce that number. So logarithm of 1,000 to base 10, or logarithm to base 10 of 1,000, as it might be particularly called or represented, is 3. So in other words, if my base is 10 and my value is 1,000, how many times do I have to take that base of 10 and have an exponent in order to reach that value of 1,000? And as we just saw, it's the opposite of 10 to the third, so the answer in reverse basically is 3. Decibels are logarithmic devices. Okay, so when we're talking about decibels, these are used as ratios. Okay, so a logarithm is a form of a ratio. We're going to be using a decibel instead of always referring to something in absolute power, as we just got done talking about, like watts or really milliwatts. Instead of referring to everything in absolute power, we're going to refer to them as decibels of something. So decibels of milliwatts, or in a little bit, we're going to talk about something called decibel of isotropic power. We'll get to that in a moment. So if we take a look at decibel, this is the ratio of relative power to the base power, which in the case of the actual decibel, the unit decibel, which is deci is tenth, and bell is a unit of measurement, so it's actually 1/10 of a bell. But regardless, the decibel is always in reference to 1 milliwatt when we're talking about it in reference to decibels of milliwatts. So we use decibels, as I just mentioned before in the last slide, kind of jumped the gun, in reference to milliwatts and later for isotropic power, represented by dBi. So I'm trying to come up with a very simple formula, and I'm going to bring up a calculator here in a moment to just demonstrate it. But a very simple formula to find for the decibel based on us already knowing how many milliwatts of power we want to transmit at. So to find the decibel, we simply take the number of milliwatts and we place that number of milliwatts against logarithm 10, and then we multiply times 10. Okay? So let's just do that real quick. Let me bring up my calculator. And let me put it into scientific mode. So here we've got logarithm to base 2. We're going to be using logarithm to base 10, okay, as our unit of measurement. And we're also going to be looking at powers. So if we have, let's say, 10 milliwatts of power, we take 10 milliwatts to logarithm 10, which is 1, because it only takes 1 times 10 to equal 10. So that gives us a value of 1, and then I multiply that times 10. So 10 milliwatts actually gives us 10 decibels of power. 10 dBm, 10 decibel relevant to milliwatts, okay? That's really almost too simple to use, right? So let's look at something else. If I use 20 milliwatts, you might think that it's going to be, just right off the bat, it might be something like 20 dBm. But you're going to be surprised to find that it's actually 13 dBm. Okay, and actually I'm just going to go back to this slide real quick and point out a couple of key numbers. Basically, anytime we raise or lower by 3 dBm, we double or halve the power respectively. So if I raise a value by 3 dBm, that is decibel relevant to milliwatt, I double the power. So we're going to find out that if 10 milliwatts was 10 dBm, then 13 milliwatts is going to be, 13 decibels is going to be 20 milliwatts. It's going to be twice the actual power. So it looks a little strange if you're not familiar with this type of math, that we're only raising by 3 units of measurement, 3 decibel relevant to milliwatts, 3 dBm, but we're actually doubling the power. So if I had 16 dBm, I'm doubling that power again. Now I'm at 40 milliwatts. And we're going to do the math here in a moment, but I just wanted to point out this real quickly. If I raise by a power of 10 dB, I'm actually creating 10 times the power. So it's kind of easy to remember. If I raise by, just remember, if I raise by 3 dB, I double the power. If I raised it by 10 dB, I create 10 times the power. So if I take 10 dBm and I raise it to 20 dBm, I no longer have 10 milliwatts or 20 milliwatts, I have 100 milliwatts. But we'll get there, back to the math here in just a moment, back to the actual calculator. If I subtract 3 dB, I half the power, or have the power. I have the power. Anyway, if I subtract 10 dB, then I create 1/10 the power. So let's go back to the calculator. Okay, so if I have 20 milliwatts, let's just start with, because we first looked at the formula for milliwatts to find dB. So if I have 20 milliwatts to logarithm 10 times 10, I have 13 dBm, okay? We're going to forgive pretty much anything beyond the decimal point, and sometimes we're going to round up a slight bit, okay? So if I have, let's say, 40 milliwatts to logarithm 10 times 10, I have 16 dBm. Remember, we took 13 dBm, which was 20 milliwatts, and we added another 3 dB or decibel, and now we're at 40 milliwatts. If I have 80 milliwatts to logarithm 10, we can see 1.9 times 10, we're at 19 dBm or decibels. If I have 100 milliwatts to logarithm 10 times 10, I have 20 decibels. So when I increase 10 decibels to 20 decibels, I actually got 10 times the power, 100 milliwatts versus 10 milliwatts. Let's go back to our slide and take a look at the opposite. So that was if we already know the milliwatts, how do we find what dB, what decibel, or decibel relevant to milliwatt, dBm? The formula to find for the milliwatt, based on already knowing the dB, is that the milliwatt is going to equal 10 times, not 10 times, 10 to the power, or 10 to the exponent, of the decibel already divided by 10. So first we take the decibel that we know, divide that by 10, and then raise 10 to the power of that result. Okay, so let's take that. So if I know the decibel, let's say I know it's, let's use something that we've already used, 16 decibels. If I take 16 decibels and I divide that by 10, I have 1.6. I need to raise 10 to the power of 1.6. So we're going to keep 1.6 in our memory. Let's just say memory plus. And I'm going to say 10 to the power of, memory recall, 1.6 is going to give me 39.8, or roughly 40 milliwatts. Okay, if we remember, let's say, let's just clear out our memory. Let's say 13 decibel divided by 10. Quite simple, 1.3. We can just remember that, 1.3. So if I take 10 and I raise it to the power of 1.3, I'm going to get 19.9, or basically 20 milliwatts. Okay? So let's say I had something like 22 decibel. We already said 20 decibel divided by 10 is 2, and 10 to the power of 2 is quite clearly 100. But let's say I had 22 decibels. What's that going to figure for? Well, 22 divided by 10 is 2.2. So if I take 10 and raise that to the power of 2.2, I'm going to get 158.4. So about 158 milliwatts, maybe 159. Or if I were to take, let's say, and go back the other way. So remember, if I already know the milliwatts, maybe I know that I want to pump out, or maybe the AP is currently tuned to pump out 50 milliwatts. If I know 50 milliwatts, I take that and make that relative to logarithm 10. I get 1.7 basically. I multiply that times 10. I get 16.9, or 17 decibel. Okay, you might need to, take and in the recording, pause and go back and try some of that math yourself with a scientific calculator. That's fine. The main things, the main takeaways that I want to remind you of are: if you increase by 3 dB, you double the power. If you decrease by 3 dB, you halve the power. If I increase by 10 dB, I have 10 times the power. I decrease by 10 dB, I have 1/10 the power. And again, if I increase by 3 dB and I double the power, and then I increase by 3 dB again, I double the power again. If I increase by 3 dB again and again, I double it again and again. So again, if I have, let's say, 10 milliwatts and I increase by 3 dB to 13, I have 13 dB, so I also have, if I started out at 10 decibels and I increase by 3 to 13, I now have 20 milliwatts. I increase by 3 dB again, I have 40 milliwatts. I increase by 3 dB again, now I have 80 milliwatts. If I increase by 3 again, so now I'm at 12 decibels, then I have 160 milliwatts. Okay, so keep that in mind. Whoops, didn't mean to exit out of that. Now let's move on beyond decibel relative to milliwatt, dBm, and let's talk about dBi and dBd. So again, decibel is just power relative to something else. When we're talking about dBm, that's power relative to a milliwatt. When we talk about, and these are industry standards, this isn't Cisco specific or anything. You probably know that, but just in case you're wondering. dBi is an industry standard for decibels relative or in reference to an isotropic antenna. An isotropic antenna is really a theoretical antenna that doesn't exist in reality at all. In theory, it's something that emits an even field of energy in every perfect spherical direction. Okay, so if you just imagine a completely round ball around a middle point, and it's emanating energy out from that in a perfect direction in all ways, then that's the idea of an isotropic antenna. Okay, we use it as a reference point, even though it's not possible to build such a perfect device. Or at least we've never done it. We use the same logarithmic scale as we do with dBm. So this allows us to actually, believe it or not, take and add or subtract dBm and dBi together with relativity to one another. So if I actually say I've got 10 dBm, or I've got 10, also, as we just talked about, 10 milliwatts of power, and I also have 10 dB, let's say 3 dBi, I can add 10 dBm plus, and I have this on the next slide, plus 3 dBi, and I have equivalent of 13 dBm or dBi. It really doesn't matter how I want to refer to it as. So if I have 13 dBm, what did we just say? That is going to be in milliwatts. Adding or raising by 3 dB doubles the power. So that's going to be 20 milliwatts of power. So that's we're going to talk about here in the next slide, and then go into much more detail in the next section on antennas. We're going to talk about how that relates to antenna transmitting power and even receiving power, also known as gain. So before we go on and talk about that a little more, we want to talk about DBD. So DBD is basically the same as DBI, except that it's based on a dipole antenna. A dipole antenna is a very specific type of antenna. It is a very common, I should say it was a very commonly used antenna. It still is today in some environments, certainly, but most people do tend to use other types of antennas in most of today's environments. You'll still see it in some environments, even new deployments, or certainly on many old access points. But those are what we commonly refer to as the rubber ducky antennas. They're basically the little rubber, somewhat flexible antennas, black. You can get them in white. They just kind of make an L shape. They connect on with the RPTNC connector. We're going to talk about connectors in the next module, but they connect onto the radio, and then they either point straight up if the orientation of the connector was already straight up, or if the orientation of the connector was pointing out to a horizontal way, they make an L turn, a 90-degree turn, and point straight up. And we typically have two of these. At any rate, that's a dipole antenna. It's got a specific radiation pattern. We're going to talk about radiation patterns in the next module. But a dipole antenna is basically dBi minus 2.14. Okay, so if we're referencing DBD, then we're referencing dBi minus 2.14. So whatever the dBi might be advertised on an antenna, maybe the dBi is 9. The antenna is built to specification and advertised as a 9 dBi antenna. But for some reason, someone asks you, what is the DBD value? You simply take 9, subtract 2.14, and that is the DBD. Okay, so we would have, 6.86, I believe, just off the top of my head. If we have the dBi, if we want to find for the dBi, but we already know what the DBD is, somebody says, you have a 6 DBD antenna, then we simply add 2.14. So plus 2.14 would be 8.14 dBi. Okay. By the way, not all vendors refer to the to the DBD value as 2.14. Some vendors refer to it as 2.2. So most of everything that you're going to deal with Cisco antennas is advertised and marketed in dBi, which is, again, synonymous or on the same logarithmic scale as dBm. DBD is not on the same logarithmic scale as dBm, decibel relevant to milliwatt. So most of what we'll be talking about is dBi, but it's just important that you understand what DBD is in case you run into it in the field, or let's say, I don't know, maybe in a Cisco exam. Okay. Finally, to round out our RF math, we're going to talk about something called effective isotropic radiated power, or EIRP. Not to be confused with ERP, Enterprise Resource Planning. So effective isotropic radiated power. The idea, or the naming behind effective, is essentially that we don't just have transmitter power, right? We also don't just have an antenna. We have the transmitter power plus the antenna, the added gain from the antenna, and not all antennas are in any way built the same. And then we also have to deal with potential cable loss. So remember, attenuation is the deterioration or decrement of a signal, the weakening of a signal across a given medium. When we were talking about free path loss, we talked about attenuation relative to distance. If we're talking about, and that's over wireless, if we're talking about power being sent out, radiated out over a cable before it gets to an antenna, If it's a very, very, very short cable, it probably doesn't have much loss at all. If we're talking about something that's maybe a half meter cable, then the cable loss is almost so infinitesimal that it's almost not even worth mentioning. If, on the other hand, let's say we have an AP inside of a building, and many APs are built as rugged outdoor APs so that they can be very close to the actual antenna. Specifically, that is so that the maximum amount of power can actually be sent directly or very closely to the antenna, physically as close as possible. Regardless, there are installations where the radio is, and let's just say a cellular network, a carrier that has GSM or CDMA cellular towers. This is a perfect example. Their radios are rather large because they're rather powerful, and they tend to be in the radio shack at the bottom. And the big, thick black cables that are running up the outside of the pole and then attaching to those panels that you see, typically 3 panels on 3 separate sides of a radio tower, cell tower, that antenna has the cable running from that transmitter down in the Radio Shack up to the actual panel antenna. It has the characteristics that it's going to lose power, okay, based on a number of things that we don't have to necessarily get to, but electrons floating out towards the edge as power is pushed, as distance is increased. At any rate, we need to take into account the transmitter power, the positive dBm, minus the cable loss, and cables are going to be rated when you purchase them at a given loss per meter. So, maybe 1 meter will be 1 dBm of loss. Maybe 5 meters will be 3 dBm of loss, whatever the case may be. And then we're going to have to also add back in the antenna gain. And this will typically, this says dBm. I should correct this to actually say dBi. Apologize about that. So the antenna gain in dBi. So if we add all those together, we get and remember the dBi and the dBm are on the same logarithmic scale, so we can add them in continuity with each other. So we add all these together, we get the EIRP, or the effective isotropic radiated power value. So let's say we have 13 dBm as power put out from the transmitter, and we have a long cable, a decently long cable that has 3 dBm of loss. So we're subtracting 3 dBm, now down to 10. Plus we have an antenna that adds back in 9 dBi. So 13 minus 3 plus 9 is 19 dBm. And again, one of those was I, but it's on the same scale, so we can say 19 dBm of effective isotropic radiated power. Okay, remember, I put down there that 20 milliwatt transmitter power is 13 dBm, so that's where I was coming up with that original value of 13 dBm would be 20 milliwatts. So just for fun, since we, let's say, have 19 dBm, let's try to figure out how much effective power that would be. So if we happen to have 19 dBm, that is, we know the dB, the decibel, but we need to find for milliwatts. We're going to take 19, divide that by 10. That's 1.9. That's going to be the power. So we're going to take 10 and raise that to the power of 1.9 for an effective power of 79.4, or we could round down to 79 milliwatts of power that's effectively being transmitted. Whoops. For the 19 dBm EIRP.